A multiple linear regression, or MLR, model is built on several key assumptions that let us treat the estimated line as a reliable guide. Linearity, the true relationship between each predictor x sub j and the dependent variable y, is a straight line when all other predictors are held constant. Think of a car's fuel consumption that rises proportionally with distance driven, regardless of speed. Independence of errors, the error term epsilon I for one observation does not influence the error for another. It's like flipping a fair coin repeatedly. Each flip's result does not affect the next. Zero conditional mean, the average error given any combination of predictors is zero. Expected value of epsilon I given xi1 through xik equals 0. This means the model does not systematically over or under predict. Homoscedasticity, the variance of the errors is constant across all predictor values. Variance of epsilon I given x equals sigma squared. Imagine a factory producing bolts where the measurement error is the same whether the bolt is short or long. No perfect multicollinearity, no predictor can be expressed exactly as a linear combination of the others. It's like trying to predict sales with both price and price after 10% discount. They carry the same information. Normality of errors, for inference errors are normally distributed. Epsilon I is distributed as n of 0 sigma squared. This assumption lets us use T and F tests. In practice, normality is less critical for large samples, thanks to the central limit theorem. Ordinary least squares, OLS, finds the coefficient vector beta equals beta 0, beta 1 through beta k that makes the sum of squared residuals as small as possible. The model in matrix form is y equals x beta plus epsilon, where y is an n by 1 vector of outcomes, x is an n by k plus 1 matrix whose first column is a vector of 1s for the intercept, and the remaining columns contain the predictors. The OLS criterion is minimize s of beta equals y minus x beta transpose times y minus x beta. Taking the derivative with respect to beta and setting it to 0 gives the normal equations. X transpose x beta equals x transpose y. If x transpose x is invertible, meaning no perfect multicollinearity, the solution is beta hat equals the inverse of x transpose x multiplied by x transpose y. Interpretation: beta hat j is the slope that tells us how much the expected value of y changes for a 1-unit increase in xj while keeping all other x's unchanged. The intercept beta hat 0 is the expected y when all predictors are 0, often a hypothetical scenario. Explanation: once we have beta hat, we need to know whether the estimated relationships are statistically significant. T-test for a single coefficient. Null hypothesis: h0 beta j equals 0, no effect. Alternate: h a beta j not equal to 0. Test statistic: t sub j equals beta hat sub j over se of beta hat sub j. Se of beta hat sub j comes from the estimated variance covariance matrix sigma hat squared x transpose x inverse. Compare absolute value of t sub j to the critical value from a t distribution with n-k-1 degrees of freedom. F-test for overall model. Null hypothesis: all slopes are 0 h0 beta 1 equals beta 2 equals beta k equals 0. Statistic: f equals SSR over k divided by SSE over n-k-1, where SSR is regression sum of squares, SSE is error sum of squares. Large f greater than the critical value from the f distribution with k and n-k-1 degrees of freedom leads to rejecting h0. In business terms, a significant t-value tells you a particular driver, for example advertising spend matters, while a significant f-value tells you the whole set of drivers together explains sales better than a model with no predictors. Multicollinearity occurs when two or more predictors move together so closely that the regression cannot tell which one is truly responsible for changes in y. Detecting multicollinearity. Variance inflation factor VIF sub j equals 1 divided by open parenthesis 1 minus r sub j squared close parenthesis, where r sub j squared is the r square from regressing x sub j on all other predictors. A VIF larger than 5 or 10 flags a problem. Analogy, trying to judge a student's performance based on both hours studied and pages read. If hours studied always translates to pages read, the two variables are redundant. Condition index. See, I compute eigenvalues lambda 1 greater than or equal to lambda k of x transpose. X, the condition index for the ith eigenvalue, is C I sub I equals square root of lambda max divided by lambda I. Values above 30 suggests serious collinearity. Remedial techniques. Number 1, drop or combine variables. Keep the most theoretically important one. Number 2, principal component regression. PCR, transform correlated predictors into uncorrelated components and regress on those. Number 3, ridge regression. Adds a penalty lambda times the sum of beta sub j squared to the ordinary least squares loss, shrinking coefficients and reducing variance. Number 4, centering variables, subtracting the mean, can help with interaction terms but does not solve collinearity. Number 5, collect more data. Sometimes adding observations that break the perfect linear pattern reduces VIF. The goal is to obtain stable, interpretable coefficient estimates without sacrificing too much predictive power. Explanation, choosing the best set of predictors is a balance between goodness of fit and model parsimony. Adjusted R-squared. Unlike ordinary R-squared, it penalizes extra variables. R bar squared equals 1 minus the fraction of open parenthesis 1 minus R squared close parenthesis times open parenthesis n minus 1 close parenthesis over open parenthesis n minus k minus 1 close parenthesis. Higher R bar squared indicates a model that explains variance well while using fewer predictors. Information criteria. ACIC information criterion AIC. AIC equals 2k minus 2 times natural log of L, where k is the number of estimated parameters including sigma squared and L is the maximized likelihood lower AIC equals better trade-off. Bayesian information criterion BIC. BIC equals natural log of n times k minus 2 times natural log of. BIC penalizes complexity more heavily than AIC because of natural log of n versus 2. It tends to select more parsimonious models. Stepwise procedures. Forward selection, start with no variables, add the one that most improves, for example lowers AIC at each step. Backward elimination, begin with all candidates, remove the least useful variable iteratively. Both stepwise allows adding and dropping in the same run. Business analogy, think of building a product portfolio. Adjusted R-squared is like measuring total market share, while IC/BIC are like accounting for development cost. You want high share with low cost. Model validation, after selecting a model, always test it on a hold-out sample or via cross-validation to confirm that the chosen criteria were not over-optimistic. Slope coefficient beta j represents the marginal effect, the change in the expected dependent variable for a 1-unit increase in x sub j while holding everything else constant. In a demand model, lnq equals beta 0 plus beta 1 ln p plus beta 2 ln I plus epsilon. Beta 1 is the price elasticity of demand. A 1% rise in price leads to beta 1% change in quantity demanded. Elasticity. When both y and a predictor are logged, the coefficient itself is an elasticity. Partial ln y over partial ln x sub j equals beta j. If only the predictor is logged log linear, the coefficient is a semi-elasticity. A 1% change in x sub j changes y by beta j divided by 100 units. Intercept beta 0 often has a limited economic interpretation if a zero value for all predictors is unrealistic. For example, zero advertising spend may never happen. In such cases, you can center variables around their means. Then beta 0 becomes the expected outcome at average predictor levels. Marginal effects in presence of interactions. Suppose the model includes an interaction term x sub 1, x sub 2. The marginal effect of x sub 1 is partial y over partial x sub 1 equals beta 1 plus beta 1 2 x sub 2. So the effect of x sub 1 depends on the level of x sub 2, an idea often used in pricing price times promotion interaction. Understanding these meanings helps managers translate statistical output into actionable decisions. such as increase marketing budget by $10,000 will raise sales by approximately $50,000, holding price constant. Explanation: after fitting a model, we must check whether the underlying assumptions hold. Residual analysis. Plot residuals E sub I equals Y sub I minus Y hat sub I versus fitted values or each predictor. Look for random scatter, no pattern. A funnel shape suggests heteroscedasticity, a curve suggests non-linearity. Heteroscedasticity tests. Bruch-Pagan or BP test. Regress E sub I squared on the original predictors. Test statistic. BP equals n times r squared sub e squared divided by 2 follows a chi-square distribution with k degrees of freedom. Second white test, more general. Regress E sub I squared on all original predictors, their squares, and cross products. The test statistic is n times r squared from this auxiliary regression, chi-square with p degrees of freedom, where p is the number of regressors in the auxiliary model. A significant result indicates that the variance of errors changes with predictors. Influential observations. Cook's distance, d sub I, equals E sub I squared divided by p sigma hat squared times h sub Roman 2 divided by 1 minus h sub Roman 2 squared. Here h sub Roman 2 is the leverage, the diagonal of the hat matrix. Values greater than 4 divided by n minus k minus 1 flag potentially influential points. DFFITS measures how much the fitted value for observation I changes when that observation is omitted. DFFITS sub I equals E sub I divided by sigma hat times the square root of 1 minus h sub Roman 2 multiplied by the square root of h sub Roman 2 over 1 minus h sub Roman 2. Absolute values larger than 2 times the square root of p over n are worrisome. Practical steps. First, identify high leverage points, large h sub Roman 2. Second, check if they also have large residuals. Those are the truly influential cases. Third, options. Verify data entry, consider robust regression, or report results with and without the outlier. Proper diagnostics protect managers from making decisions based on a misspecified model. Regression is often used to forecast future outcomes, not just to explain the past. Point forecast. For a new set of predictor values x new, the predicted mean response is y hat sub new equals x new prime times beta hat. Confidence interval for the mean response gives a range where the true average E of y given x new is expected to lie with a chosen confidence level, for example 95%. Y hat sub new plus or minus t sub alpha over 2 comma n minus k minus 1 times the square root of sigma hat squared times x new prime left parenthesis x transpose x right parenthesis inverse x new. The term under the square root is the standard error of the estimated mean. Prediction interval for an individual outcome accounts for both the uncertainty of the mean estimate and the random error of a single observation. Y hat sub nu plus or minus t sub alpha over 2 comma n minus k minus 1 times the square root of sigma hat squared times open bracket 1 plus x nu prime left parenthesis x transpose x right parenthesis inverse x new close bracket. Note the extra 1 inside the brackets. This makes the interval wider than the confidence interval. Business example. A retailer estimates quarterly sales using advertising spend, price, and seasonality. Using the fitted model, they plug in the planned advertising budget for the next quarter to obtain y hat sub new equals $2.3 million. The 95% confidence interval for the average sales is $2.0 to $2.6 million, while the prediction interval for the actual quarter's sales is $1.5 to $3.1 million, reflecting random market shocks. Okay tip. Always report both intervals when decision makers need to understand the range of likely outcomes. Explanation. Here are typical exam-style questions and the trap students often fall into. Sample questions. Given the following OLS output, test whether the coefficient on x2 is statistically different from 0 at the 5% level. Show the calculation of the t statistic and state the conclusion. Pitfall: forgetting to use the correct degrees of freedom, n-k-1, or misreading the standard error column. Explain what a VIF of 12 means for x3 and propose 2 ways to address it. Pitfall: mentioning only that VIF greater than 10 indicates a problem but not linking it to inflated variance of beta hat 3 or suggesting remedial actions. drop variable, ridge, etc. Derive the 95% prediction interval for a new observation with x equals 5, given the model estimates below. Pitfall: using the confidence interval formula instead of adding the extra variance term, the one inside the brackets. Compare two models using a IC and BIC and decide which one you would choose. Explain why the criteria may disagree. Pitfall: stating only the numerical result without describing the penalty terms, 2k versus ln of n times k, and the preference for parsimony. Interpret the coefficient of ln of price equals -0.75 in a log-log demand model. Pitfall: saying it is a negative relationship without noting that it is a price elasticity of -0.75. That is, a 1% price rise cuts quantity demanded by 0.75%. Common pitfalls across topics. Mixing up R-squared and adjusted R-squared. Adjusted R-squared can decrease when an irrelevant variable is added. Forgetting this leads to overfitted models. Assuming causation. Regression shows association, not cause-effect, unless the study design justifies it. Neglecting diagnostics. Skipping residual plots or heteroscedasticity tests may invalidate inference. Incorrectly handling categorical variables. Forgetting to create dummy variables or using the wrong reference category leads to misinterpretation. Rounding errors. Reporting coefficients, t-statistics, or p-values with insufficient precision can change a conclusion. For example, p equals 0.051 versus 0.049. Study advice. Memorize the key formulas OLS estimator, t-statistic, f-statistic, VIF, OIC/BIC. Practice interpreting output tables. Know which column is the coefficient, SET, p-value. Run a full diagnostic checklist after every regression. Residuals, VIF, heteroscedasticity, influence. Use real-world examples, sales, finance operations, to translate abstract numbers into business insight. When in doubt, write down the underlying assumptions. Many exam points are awarded for acknowledging them.